Hello everyone, we are from Group 16 and we are going to present about the bioamplifier and filtering circuits for biomedical signals. I am Toh Ka Peng with metric number 22004663. Now I will present about inverting amplifier. So these are the schematic diagram and also the implementation photos for the inverting amplifier. After the simulation, we can see that the output signal is actually the inverted version of the input signal. Besides, the gain is -3, so the output signal will have 3 times the amplitude of the input signal. From the practical results, we can also see that the output signal is the inverted version of the input signal. Besides, the peak-to-peak voltage of the output signal is 11.5 watt, while the peak-to-peak voltage of the input signal is 3.4 watt, so it's almost the 3 times of the input signal. Inverting amplifiers has been widely used in right leg drive, where the phase of the common mode voltage in the right leg will be flipped by 180 degrees and input back into the circuit's common mode point to eliminate the common mode interference. The two examples of the right leg drive are electromagnetic flow meter and also the ECG machine. Next is the passive low pass filter. So these are the schematic diagram and also the implementation photos. As the cutoff frequency is 106 Hz, from the simulation results, we can see that the gain at 106 Hz is -3 dB. Besides, we also insert another V-noise, which is the voltage with high frequency of 3 kHz compared to the V-in of 30 Hz. Vt is the summation of the V-noise and the V-in. From the V-out, we can see that the V-noise has been attenuated and leave only the V-in. From the oscilloscope, we can see that as we adjust the frequency from 10 Hz until 1 kHz, the peak-to-peak voltage of the output signal has been decreasing and the lagging phase shifting has been increasing. Passive low-pass filter can enhance the signal quality by passing the low frequencies which are desired and attenuates the high frequencies. So they are widely used in EMG machine and also the pulse oximeter.
Hi, my name is Owen. My metric number is 22004630. Now I'll be presenting the active bandpass filters in 7 key topologies. Our group designed a second-order Butterworth bandpass filters by cascading one low-pass filter with a cutoff frequency of 884 Hz and followed by a high-pass filter with a cutoff frequency of 1061 Hz. So the center frequency of this active bandpass filter is 1000 Hz. And this diagram shows a lab circuit that we have constructed in the workshop. Now looking at the simulated transient response of the active bandpass filter, we can see that our designed second-order Butterworth bandpass filters have successfully rejected the V-noise 1 having the frequency of 200 Hz and also V-noise 2 having frequency of 3 kHz, and only pass the desired input frequencies having the frequency of 1 kHz as shown in the V output here in the diagram. Now it shows the body plots of the bandpass filters. We can see the peak gain of 2.82 decibels and zero phase shift at the center of frequencies, 1 kHz. However, the peak gain of 2.82 decibels does not align with the theoretical calculations. The reasons for the lower peak gain values compared to the theoretical calculated value is due to the narrow bandwidth. The 200 Hz bandwidth has caused the signal to be attenuated at the center frequencies, and this is because the cutoff frequency is too near with the center frequencies. And the Butterworth filters having the Q factors of 0.707 it is not a sharp rule of curve that can achieve the maximum peak gains at such a narrow bandwidth. And here is the practical transient response of our constructed bandpass circuits in labs. It rejected the 100 Hz signals with the leading phase shift, and it passed the signals above the cutoff frequencies and also at the center frequencies. It also shows the same gains compared to simulation results. Next, for the signals above the cutoff frequencies, it shows that the bandpass filters have successfully attenuated the signals, and also the phase shift is similar to the body plot, which is lagging. Regarding the biomedical applications of the bandpass filters, the Butterworth bandpass filter is useful in passing on a spectrum of signal containing the desired informations, so it can reject the higher or lower frequency noise, and especially for the power line interference. So it is used in analog filterings and also digital filtering. Now I'll be presenting the design and safety consideration when applying these circuits to patients. In most of the case, the circuits that were chosen, such as the inverting amplifier, passive low-pass filters, and also the active band-pass filters, they are not used solely to the patients. Instead, they are combined together to use as a biopotential amplifiers. And these are the basic requirements that we need to consider when designing the biopotential amplifiers. In terms of performance, we need to have high input impedance, low output impedance, optimal frequency response, the high common mode rejection ratios, and high enough and adjustable gain of the amplifiers. And in terms of safety, we need to isolate and also protect the circuitry. Here it shows the functional block diagram of a common biopotential amplifier. Each of the block has its own roles to meet the basic requirements as mentioned before, and to better illustrate and explain the concepts of the design and safety consideration when applying the circuits such as the inverting amplifiers and also filters to the patients, ECG is used as an example of the biopotential amplifier in the following presentation. First of all, talking about the amplifier protection circuits, why we need to use an amplifier protection circuit is due to the reasons that electrical transients might happen when ECGs or any other biopotential amplifier is used simultaneously with other electronic device on the patients, such as the electrosurgical units and defibrillators. If one of these units have faulty conditions, leakage current will enter into patient's body back to the ECGs or the amplifier circuitries back to the ground, and it will cause microshocks and macroshock hazards. Thus, having amplifier protection circuit is important to protect both the device and the patient itself. And here it shows the common circuit protection methods is by connecting two terminal voltage limiting device between the patient electrodes and also the electric grounds. One of the examples is by using a back-to-back Zener diodes. Other than that, the most common methods to ensure patient safety is to apply isolation circuits. It is to isolate the patient from the high voltage input circuitries by breaking the ohmic continuity physically between the input and output stages. So the isolation circuit has the high ohmic isolations. It usually is over 10 mega ohms, and high isolation voltage usually over 1500 volt ACs according to the IEC 60601 standards, and it has a high common mode rejection ratio above 100 decibels. And figures here shows is the capacitive isolation circuits that are often used in the biopotential amplifiers. It is having the peak isolation voltage of 8 kilovolts and the bandwidth allowed for the frequency to pass through is 70 kilohertz. Next, to ensure both the safety and also the performance of the biopotential amplifiers, a driven right leg system is usually used. It involves an auxiliary op-amp, which is usually inverting amplifiers that can invert, amplify, and feedback the common mode voltage back to the right leg and reducing the common mode noise. And it also can unground the patient if a high leakage current saturated the auxiliary op-amps, thus preventing the patients from experiencing shocks. Here are some of the characteristics that we need to consider for the preamplifier to work optimally. So to ensure that high input impedance, high CMRR, and also the low voltage gain at the preamplifier stage, we often use the instrumentation amplifiers because we can control the low voltage gain by just adjusting the RG values. And the gain at this stage is around 25 to prevent signal saturations. When using low-pass RC filters, such as in the case of RFI filters, we need to carefully define the cutoff frequencies. So in this case, we need to define the cutoff frequencies to around 1.2 kHz to maintain the cutoff frequency of 100 Hz at the processing stage. Lastly, to use an active band pass filter, we need to ensure the frequency response of the filter is having a frequency spectrum compatible to the collected signals. So we need to carefully define the cutoff frequencies of the filters. For example, in the case of ECGs, the lower cutoff frequency is usually 0.5 Hz and the higher cutoff frequency is usually 100 Hz.
One of the professional responsibilities in circuit design is the competence and expertise, which involves the responsibility of engineers to utilize the necessary knowledge and skills to design safe and effective circuits. Besides, the diligence and thoroughness are also one of the professional responsibilities which emphasize the need of meticulous design, simulation, and testing. For instance, the designed electrical equipment should also adhere to related local standards such as IEC 60601, MS ISO 14971, and so on. There are also professional responsibilities that discuss the responsibility of engineers to take ownership of the design and be accountable for their performance and safety, with clear and transparent information being documented. When designing biomedical circuits, ethical practice is crucial, starting with patient safety as a top priority throughout the design process. Every design decision, from component selection to power supply isolation, must prioritize the well-being of the patient. This aligns with the principles of beneficence and non-maleficence, which act in the best interest of the patient and avoiding harm. If the device involves processing or storing patient data, it is also important to uphold privacy and data security. Last but not least, ethical design also involves social responsibility, considering how accessible and equitable the device will be for different groups within the society. In the simulation stage, we also faced several challenges. One of the issues was defining values for components, which the simulation components consist of various complex settings to be set and defined. Next, we also had to be very careful when connecting components. If any were left unconnected, it would result in the floating circuit errors after running transient analysis, which could be tricky to trace. Another important aspect was grounding, where all components, including voltage source, has to be properly grounded. Fail to do so would cause the simulation to fail or produce an inaccurate result. During the practical implementation of the circuit, one of the challenges that we face is the limitation in component availability, so we had to adjust our pre-designed circuit based on what was accessible. We also recalculate the theoretical value of the cut-off frequency and gain to compare them with the practical circuit outcome. We also experienced unfamiliarity with the lab equipment. The circuit connections were quite complex, so it took us more time to connect everything correctly. Extra effort is given in assessing every connection to avoid errors and ensure the circuit worked properly. Another challenge was dealing with faulty components. For example, an LM741 op-amp malfunctions. We had to identify the faulty components and replace them accordingly.
Safety is very important for those who develop or operate the medical device with amplifiers. To clinicians, there should be no overheat issue to prevent the burning of the components, and the maintenance or servicing of the device should be done regularly. To patients, device should have a complete grounding system to prevent electrical hazards, and it should pass the requirements of leakage current test as per requested by IC 60601 and quality management system as per requested by ISO 13485. To designers, they should alert on the datasheet of the components used for the circuit construction and turn off the power supply when not in use. They should also calibrate the measuring device before testing to ensure the accurate results and wear ESD restraint when implementing the circuit. Regarding the documentation standard, the first one is the IC 60601 that is used to ensure the safety of patients when using medical electrical equipment by minimizing the risk of electrical hazards. The second one is the IC 80601 Part 2, which is the expansion from IC 60601 Part 2. The third one is IC 61010 that provides safety guidelines and requirements for electrical equipment used in various settings, including laboratories, measurement and control system, and similar environments. Next, we have ISO 13485 that provide global standard for medical device quality management system, and the last one is the ISO 14971 that specify terminology, principles, and process for risk management of medical device. After this project, we are able to learn about the application of op-amp in real life, where it can use as the filters to remove interference and electrical noise in signal amplifications and also in analog signal processing. Besides, we have the chance to hands-on for the op-amp circuits implementation, where we use the LM741 to construct different types of op-amp circuits and real-time observation on the waveforms from the oscilloscope. Lastly, we have improved our skill to simulate op-amp circuits and observe their result using TINA-T.
After completing the projects, I've gained insights on the difference between simulations and practical circuits. So in simulations, it is suitable for having a quick understanding on the circuits, but in practicals, we need to consider the errors and tolerance of all those electronic components and their effects on circuit designs. And I've transformed textbook knowledge into practical use, gaining deeper understandings on how to use the op-amps, filters, the body plots, and transient response. Lastly, I've gained troubleshooting experience during the circuit constructions, and we have collaborated with each other to solve the problems.
Through this project, I gained a deeper understanding of filters and op-amps, including how to connect different components to form various types of filter circuit and how to calculate important parameters like gain and cut-off frequency. On the practical side, I had hands-on experience constructing circuits on a breadboard. This allowed me to learn the correct techniques for connecting and grounding components while also becoming more familiar with the lab equipment. It was also a valuable opportunity to apply theoretical knowledge in a real-world setting. I also developed better troubleshooting skills, learning how to identify and fix common circuit errors. Working alongside with my teammate also improved my communication and collaboration skills, especially during problem solving. So that's all from Group 16. Thank you so much.